when we are starting from the lower point to the upper point. So we are climbing up. So our today's topic will be basically on these aspects of vertical curvature and the gradient. You may ask yourself a very simple question that why do we need a vertical alignment? Why do you need a vertical alignment design? Of course, you remember previously we have seen that horizontal alignment is very important because we want to change the direction. Also, vertical alignment is very important because sometimes we want to have some minimum requirements so that our vehicles can move without any difficulties. And also we have to cope with the terrain condition. So normally vertical alignment design will help us to have the components of vertical curves. So, or maybe what you can say, the components of or features of the vertical curves. Secondly, by vertical alignment design, we will be able, of course, to establish the minimum and the maximum values for the gradients. You know that the gradients will be defining whether if the vehicles can move up or down safely. You understand? Because if the gradient is too much, maybe particular types of vehicles may not be able to climb, to move up. Or if the gradient is too much, sometimes vehicles will be experiencing some difficulties in braking. So that's why you need to have the maximum, the minimum values of the gradients. And then you know that our roads are passing through different villages and through the various places like in urban centers, in rural areas, and then in some settlements. So there are some guidelines which have been established by what we used to call the design standards, so that we try to minimize the problem of safety or the problem of accidents that may occur if some guidelines are not followed. By the vertical alignment design also, we'll be able to, of course, to discuss some of the particularities like a climbing lane or what we call the clearance, vertical clearance. These points will come later, but keep in your mind that vertical alignment is very important because our roads will be running, of course, in a vertical plane from the start till the end. Vertical alignment, normally we have got two major components. The first component is about the curve, the vertical curve, or the curves which are designed in a vertical plane. Then the second major component of the vertical alignment is about the gradients or the grade, the slope expressed in percentage. Basically, two types of curves exist as far as vertical alignment is concerned. Normally, we are defining the vertical curvature using either simple curves, which are circular curves, or using what we call parabola. Normally, the curves which are provided for vertical alignment are useful and very important to provide a kind of smooth transition between consecutive gradients. You know, it's like if you go through a point A to B in a vertical plane, the ground surface may be irregular. So you need to connect the points with the vertical curves so that you are making now the ground somehow smooth. So in that case, you are using now the vertical curves. In practice, using simple parabola is the mostly adopted, where we are using a parabola. You remember from your mathematics background, if you try to look at this equation here, this is an equation of a parabola whereby we have f of x or y is equal to ax squared plus bx plus c, whereby the elevation of BVC, beginning of the vertical curve, this can be considered as a constant. And this is what you have had in mathematics, in engineering mathematics, whereby a parabola is defined by the equation of ax squared plus bx plus c. Yeah, if you still remember, and I think it is still in your mind. So a simple parabola is most of the time used, but also a circular curve can be also used, but in a vertical plane. Of course, we have got two major types of vertical curves. A curve can be a sag curve or a crest curve. What does it mean by a sag curve? A sag curve, this means that the curve starts from up and then goes down, then it goes up. Then a crest means you start from down, going up, and then go down. So I will be showing maybe the sag and the crest using some of the diagrams. Let me see if, yeah, for example, this curve, you can see how it is. This is a crest. It means you're starting from the lowest point, you go up, then you go down. This is a crest. Then, if it is now in the opposite direction, this is a sag. Sag means you start from the highest point, you go to the lower point, and then you go again to up to the highest point. So sag. So you can have sag, and then you can have crest curves. From the design of vertical alignment, of course, we have got, as I have said, we have got the simple parabola, and the simple parabola normally, you remember the equation of f of x is equal to ax squared plus bx plus c. Normally, a is known as a gradient, and it can be expressed by taking into account the grades of the connecting lines, the grades of the connecting line. So you have maybe the line 1 and the line 2, which are connecting then to make a vertical curve. So in that case, the first line will be having a gradient, let us say J2, and then another one with the G1, G2, G1. Then if you make the difference by the distance that separates the two gradients, now you can have the gradient. Normally, the equation of ax squared plus bx plus c, a is considered to be as a gradient. This slide here is trying to show you what are the components of the formula, or maybe the component of the relation that is used to define a simple parabola as far as vertical alignment is concerned. Of course, the rate of change of grade, or like a gradient, it is R. Then J1 here is standing for the grade of the starting line, the starting part. And then J2, this is standing for the ending grade. Let us try to look on the diagram. I'm trying to show the diagram. Yeah, for example, you can see this line. This is line which starts from here and it goes up, and this is another line. So of course, these two lines, they are meeting, and they are making, of course, a crest. So we need to introduce a curve between them, because you cannot have a road which goes this way and then, because here it is a problem. So you need to make it smooth. So, of course, this line will be defined by its gradient, and then this one also is going to be defined by its gradient. That's why you have here J1, then you have J2. So this is the gradient for this line. This is the gradient of this line. Now, if we come back in this formula, we can see that we have the length of the curve. This is the length from the start. You see, you have the beginning of the vertical curve, and then you have the end of the vertical curve. So the curve should have a start and then should have also an end. So the start and the end should be well defined as far as in the project when we are dealing with the design. X and Y will be the points whose computations will be done based on the values of the design. X, of course, it is the measurements of the distance in X direction or in X ordinates. Then Y will be the measurements of values of elevation in Y direction. Let us consider the diagram on this slide. If we try to look on this slide, the measurements that will be doing along this x-axis will be considered as x values. And then the measurements in the vertical plane will be considered as the y values. For example, on this example, from here up to here, maybe this is a value of x1. From here, going here, this is a value of x2. So for each value, there is a corresponding value of y. And that one, of course, is facilitated by the equation which was shown there. You can see if you try to look at this equation seems to be somehow tedious or complex. And this question, for the design purpose, it has been simplified. That's why this question is almost similar with this one that has been simplified. You can see in this equation, only what is required is to have the values of x's and then the values of y will be computed as per the formula itself. So here, this value j, this will be representing the difference between, of course, the gradients of the lines that I have said previously. If you have, for example, J1 and J2 as the lines, the difference in between will be giving us this value. And this will be the same as the one that we have had, like R. Then L, this L will be the estimated length of the vertical curve. Length of the vertical curve. And then this X and Y will be the values which will be measured along. Are we together, class? Will be the values which will be measured along the curve. Of course, I'm planning, let us hope that by next class, we'll be having our physical class, and I will try to draw on the whiteboard and then show you how these values can vary. Having a value of X, then what is the corresponding value of Y? It is, then you can, at the end of the day, you can have now the whole curve which has been drawn. This formula that you can see here is a simplified format of this formula. All of them are equation or are function for a simple parabola. Okay? Then if you try to look, for example, for this crest curve that we have here, we can see for the curve has got what we call the beginning of the vertical curve that is known as BVC, and then it has an EVC, which is the end of the vertical curve. So our curve will be going through this point. So this is the value here. There is a corresponding Y1, because from way up to here, we have X1. Then if you now you replace it in the formula that we have seen, Now we'll be having the corresponding value of y1. Here, from way up to here, you have x2. Now this will be the value of y2. So you can see there is a maximum value of y from which if you increase the value of x, y will be decreasing, decreasing till you reach the end of the vertical curve. For example, from this diagram, you can see that if the value of x increases, if the value of x increases, it starts by increasing the value of y, but it reaches at a particular point where the value of y is at the maximum. Then the more you increase the value of x, the value of y will be decreasing, decreasing till it comes back to the lower level. It can even go up to the negative value because, for example, if our origin is here, you can see, for example, that here, at this point, the value of x maybe is x4, but the value of y is 0. Here, the value of x is 0 and the value of y is 0. Here, the value of x is x1 and this is the value of y1. Here, from here, coming this way up to here, this is the value of x2 and if you replace the value of x in the equation, now you'll be having this value of y. You can see, I think this one seems to be the maximum value of y. Then the more you increase the value of x, you will be having the less value of x. Okay? So let me try to use paint and then I try to show you how these changes for the curvature are happening. Just wait a moment. The moment. Okay. Trying to share with you. I'm trying to share with you another screen. Another screen. Trying to share with you another screen. It is this one. Can you see the empty screen? I think, yeah. Now, let us assume that I'm drawing actually. Let us assume that we have a rod. We have this is a straight section, and you have another section which goes this way. So, in engineering, in vertical alignment, of course, this is the vertical plane. We need to connect. For example, this point. Sorry, I'm looking for the point. Trying to connect. Let us say we have this point here. Just wait. This point here and this one. So this is the beginning of the vertical curve at this point. At this point, try to make it bigger. Then this is the end. So you remember our equation is that y, let me use the black color. Y is equal to over 200 x square I'm trying to use the paint. This squared. This squared, huh? So meaning that this question is also equal to G over 200 times x square. You can put L here. L here. So it means that if you have the origin, let's put our origin here. Because there is a beginning of the vertical curve. This is what I was telling you. This is a y value. This is a x value. So okay. So now for a particular value of x, let us say from here up to here, for example, this distance, let us call this one x1. Of course, the x1 will be put in the formula, and then we have, so we have like a table. So we'll be having a table with the values. These are the x's, these are y's. For x1, we have y1. For x2, I'm having y2. For xn, we are having, of course, yn. This j value, this will be called, of course, this line going this way, it has a sloping, and this was nothing another. This, of course, this is a gradient, or you call it just a grade. Is another grade. So this grade, for example, it is of a particular percentage. Let us say J1. This is another grade, slope of maybe J2. You know, if you go up, this is a positive. When you go down, this is a negative. So we are taking the algebraic sum. So it means J1 minus J2. Because this will give us that value. Because of course it's algebraic sum, I put minus because this may be negative because it's going down. If this is going up, this is going down. And then the L will be the starts, expected starts, and here. So the distance L. Then for a particular value, we have the value of y. For example, for x1, measuring here, maybe we have the y value somewhere here, which is corresponding to this. This is the y1. Then if we have x2, maybe up to here, this is the x2. Now we'll be having a corresponding value, maybe somewhere here. This is a point. Then for x3, you'll be having also another value, and so on. So at the end, we'll be joining these points. and then the curve is generated. Oh, sorry, sorry. I'm trying to, let me try to draw smoothly. Maybe we'll be having something which looks, no, 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 no. Drawing is not easy. I'm trying to draw, maybe it means another color. So the curve, no, 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 no. It means just simple. So we'll be having something. So the curve, of course, I apologize because of my hand drawing. So I'll be joining those points. And then now the curve can be got. So this will be the vertical curvature. Of course, in the next class, physically, I tried to have an example and execute this one. Yeah, maybe this one was due to, maybe the point is somewhere here. Point is somewhere here. Another point is here. The point is here. The point is here. So now our curve will be started. So this is the vertical curve, which is designed based on this. Of course, we as engineering surveyors, the principle that we should have is that the vertical curvature that we have should be, of course, of a simple parabola. But it is not always the case, because we may have some cases where this curve is not a parabola. In that case, it is a vertical, it's a circular curve, not a parabola curve, circular curve. In that case, we have another use of what we call K value. Those are some constants. We are going to see it on the next slides. So I think this is what I want to show you when we want to use this relation for simple parabola. Is for simple parabola. Parabola. So now let me go back and then share with you the window, another window. I want to share this. I stop sharing this one. I want to share with you another one, which is this. Okay. So, are you together, class? I know it's somehow difficult, but don't worry. Don't worry, you have opportunity to come and then maybe you can draw to on the board. But this is the formula that I was using, how to produce a vertical curve. So please keep in your mind that a vertical curve, it is drawn in a vertical plane. And the important things that you have to have with the vertical curve is to have the grade of each line connecting. Maybe the first line and the second line. You remember I was showing you there. Then secondly is now to compute the values of y's as I was showing you. Now let's go ahead. This is the case. This is the case. Of course, this is a curve which is a sag. It means the summit is down. You can see the lowest part is down, but for the crest, the highest part, this actually looks downward, if you can say. The other one looks upward. That one was upward. So this is a downward. It is a sag curve, and these are the measure curve that we can have. Then another thing that we can have, I think also this one I have to draw. negotiate with you. Just wait. Um, I'm trying to find. Yeah, I'm sharing. I'm sharing. It may I want to share with you another. Yes. Yeah, we can have the situation, for example, where we have the gradient which goes this way. You see? Let me try to let me draw it properly. You have the first road goes this way. Then here we have another one which is going up. So in this case, you can see you go up. You see, you go up, and then here again you go up. You see? So in this case, now you'll be having a curve. You'll be having a curve, vertical curve, which looks like this. Just wait. Just wait. Maybe this is the beginning. Then you'll be having a curve which looks like this. Maybe. Also, just wait. Let me use red color. You can have something which looks like this. So this is the beginning. This is the end, for example. Okay. Then you can also have a situation where, for example, you have something which goes this. Sorry. You have the start like this, and then it goes down. This is the situation that we are having. Up, down. So this is it. Plus, let me look for the sign here. The symbols. This is plus, is negative. This is a plus, this is a plus. Then you can also have negative, negative, which is drawn like this way. You have this way, and then it goes here again. You see? This is a situation where you can have the road which goes down, then it goes down too much. Actually, this is too much dangerous. Yeah, you have something which looks like this, down, negative, negative. This situation also can be happening when you're dealing with this negative, negative, when you're dealing with the vertical curvature. In that case, for example, the curve, let us say maybe the curve is between here and here. So the curve will be connecting those 2 points. Maybe we are doing something which looks like this. Okay. Yeah. Connecting this way. And also, because you can have a plus, 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 negative, 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 and then also you can have, yeah, these are the crest types that you can have. Normally, these are the crest type, crest type, crest types. These are the crest types that you can have. These are the crest types that you can have. Um, sorry. Trying to connect. Yes, these are the crest type that you can have. You can have also the situation where you have got the sag. So these are the plus, 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 negative, negative, negative. Then you can have sag. Sag, it is in this format. Now you have, so let me use black color. Can have this and this. So you have negative, and then this one, this is a positive. Okay? So you're having a positive, positive, positive. Yeah. So here, for the sag curves, you can have the situation like this: negative, positive, or you can have another situation like this. We have this, and then no, no. We have this. Now we have a negative. No, no, yeah, yeah, no, no. Let me. So we have something which is like this. But this is the same, huh? Negative this way up. I think this is the same as the previous one. Here we have cos. This is positive. This is positive. Can see, but the curve is sag. The curve is sag because you can have the points here. Let's say we have some of the points maybe here and here. They want to connect with the curve. Yes. But here we have like this. Yeah, maybe you want to connect by this. Okay. And what another type that can we have? Any idea maybe? I think you have kind of plus, negative, plus is a sag. And you can have a situation. Otherwise, if you can go like this, go down like this. Yes, that one also can happen. You can also have a situation like this. This goes down, then it continues to go down. Something like this. This will have a curve which can connect also here, maybe, and here. Maybe it can connect by this curve. Okay, so here we have negative, then another negative part. So we can have just uh, plus, plus, negative, negative, then plus, see, negative, negative, plus. I think what about this one? I think this one was a positive. This one was a positive, I think. This was negative. Yeah. We can have just two positive or two negative sides, and then you can have just a mixture of the two. So you can see these are the three types of sag curves, and these are the three types of crest curves. So, class, this is what I want to show you as far as these crest curves and the sag curves are concerned. So now, let me go to the next slide. Let me go to the next slide, and then I share it with you. Stop sharing. No, I share another one, which is this. Share. Yeah, this is a situation I think I've shown to you. And we continue. Of course, this is something new that I want to introduce because previously the design that I talked about was concerning only the what you call the simple parabola by the parabola using that equation. But here we can have some vertical curves which are not parabola, but which are just a simple circular curves. So in that case, we'll be having what we call K values. K values are the the parameters that we use to transform some which we are supposed to be parabola curves, but we will be drawing them as simple circular curves, but in a vertical plane. This table here, I'm having a table here which has been produced for the purpose of designing the curves in the vertical plane, whereby the design speed parameters are used. For example, if we have like a design speed of 60 kilometer per hour, now we'll be designing a curve with a k value. These are the minimum value uh, uh, for maybe for crest. You see, this for crest, this for sag curves. So for crest, for example, if the design speed is 60, k value, actually k value, these are like the degree of curvature. The degree of curvature, that's how I can define it. So k value will be defining how the curve is, for example, somehow difficult to turn through it. Uh, the small the value of k, the difficulties sometimes you may experience to go through the curve, But as you know, we have the crest curves and you have the sag curves. Crest curves are up and down, and the sag are down and the up curves. So if we consider, for example, a design speed of 60 kilometer per hour, will be allowed to have the minimum value of k, which is 11. So in this case, if you want to design a curve connecting those 2 points, normally we take the value of k and then we multiply. There is a relation that we use. Sorry, I'm trying to. Yeah, for the length, then we multiply with the length of the curve. So let me go to the example. For example, if you have like a k value which is 13, and then the design speed was 100. So in that case, if now you want to replace the the parabola with the circular curve, now you'll be using this k value. Then, of course, you'll be multiplying it with the value of 100. The value of 100. So let us go back and then see in the table what they predicts. They predict. Just wait. I want to come to these graphs. So, can you see these graphs? Yeah. So on these graphs, we have got some parameters. There are different parameters. This along this axis, we are having what we call the length of crest vertical curves. What does it mean by the length of the vertical crest curve? The length of the vertical curve is the length from where the curve starts to where the curve will be ending. Then along this axis, which is y, you are having what you call the algebraic difference in grade. You remember the algebraic difference in grade? Maybe you have the grade this way, so you have the difference. You may have plus, plus, so you have plus, negative, you may have negative, negative, something like that. So then on this chart, these are the charts which are provided for the design. You can see you have what you call the design speed, and then you have what you call the K value. K value, normally, these are the values which will be helping us to define how the curvature of the curve is. So K value in vertical curves will be helping us to, of course, uh, define to define how the curve is abrupt, if you can say how the curve is abrupt. It is just like a measure of abruptness, how difficult it is to go through it. I think you understand what I mean. So the degree. So if the K value uh, is high, uh, and another one is low, the level of abruptness or the level of negotiating or of climbing and turning is not similar. In some cases, it is very simple. In some other cases, it is very difficult. So now, if we try to look on this graph, just forget about this one. Just let us consider the x-axis, the y-axis, and these values that you can see. So from this one, what is important for us is, for example, to design what's the minimum length of the curve that we may have in some cases. Suppose you have the algebraic sum difference, maybe let us say over 6, algebraic sum of 6. It means the first gradient minus the second gradient, you get 6%, for example. So now you come to this line of 6. Okay. So from this line of 6%, you see we are having different design speeds. So for example, you have 30, 40, 50, 50, 70 kilometer per hour, 80 kilometer per hour, 80, and so on. So now, for example, let us assume that in our design, we are having a design speed of maybe 70. This is 6. Of course, if you have 6% and then the design speed is 70, now you are coming up to this point. You see? So you have the algebraic difference, which is 6%. Then you are coming to the design speed of 70 kilometer per hour. Normally, the minimum length of the curve should be 100 in that case. So if you have this, then you have what this. Now, if our design speed, for example, is let us say 60, so I think you'll be having around 50 meters, maybe 050, maybe 70, because the 50, 60, 70 meters. That will be the length of the crest vertical curve. So don't worry about these curves I show you. Then the degree of curvature you can see, it will be very, 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 very small. In that case, if the algebraic difference in a grade is 60% and having a design speed of 60, coming to this graph, we'll be having something which is around 70 meters as the length of the curve. And then the K value is 11. Is 11. Is 11, you can see. So meaning that going through the curve, it is not easy because the level of abruptness of the curve is very tough. The same thing, of course, these two curves, this is for crest curve and this one is for sag curves. So the reading and the use is the same, but they are applicable for different types of curves. Now, the K values, as I have said, for example, in Rwanda, we are using the Rwanda Transport Development Agency Design Manual, whereby the K values are shown in table 7.1. There is in these slides, there's a table 7.1 whereby that table will be giving us the value of k if you don't want to use the chart. You remember previously, I was using the charts to see what is k. You understand? So there are two possibilities of getting the k values. You can get the k values, which will be defining the abruptness of the curve using the charts, like the previous one that I was using, or you'll be using some design tables. Let me show you those tables. Those tables are here. You can see table 7.1, the 7.2. These are the curves. So these are the tables which are useful to establish the values of k. And then these are the charts. And this also is another chart. Okay. Now, and then the value of k, we should be very careful because sometimes we need to define the value of k based on what we call the stopping sight distance or passing sight distance. So the distance which is minimum so that you can overtake, for example, or you can see clearly in front. Otherwise, you may have the curve which does not allow you to see properly. You are climbing, but you cannot see in front of you. That's the problem that we may experience if we do not properly design the vertical curves. So now, let me go to the next slide. Let's go to the next slide. So k value, if we try to go mathematically, k value is a value, of course, that will be defining how difficult is to go through the curve, or simply we say k value will be a value which will be defining the level of abruptness, making it simple or difficult to go through. So mathematically, k can be expressed as L over A, whereby L is the length of the vertical curve that we have, and then A is the algebraic difference of the two grades. So if vertical curves are expressed as a circular curves instead of parabolic curve, the correlation between k value and the radius is in such a way that the radius will be equal to 100k. So which means, for example, if you have k over 13 for that particular parabola, we can replace that parabolic curve with a simple circular curve with a radius of 1,300. Are you together, class? Are you getting me? Let me repeat it again. When I talked about the vertical curves, there are three things, first of all. The first thing with the vertical curve is to know that curves are designed using two different gradients, because we are joining two lines, the incoming and the outgoing. So you have the coming and the outgoing. Let me try to draw it. Yeah, let me share. Let me share this one. Let me share this one. Stop. I'm sharing a new one. I hope that you are seeing it. Let me make a new. So we have this gradient, and you have, for example, this one. Okay. So from here, let me put the letters. Maybe here we have the point A. This is B. This is C. So maybe you want to connect these 2 points from here and here with the curve. Or you want to connect from here to here. So if you use, for example, if you connect, or maybe you can connect even from here up to here, it means different curve. So you have the red, we have the green connection proposal, then maybe you have the blue connection proposals. So if you use the blue connection proposals, for example, you will be having something which maybe looks like this. Can you see? If you have the green proposal, you'll be having something maybe which looks like this. If you have the red proposal, you'll be having something which is like this. You can see, let me go to this blue. Practically, the blue connection is simple because you don't have to climb too much. So it means you have the length of the curve. So K is equal to L over A. So maybe this one is a positive. I think this is a negative because we're going down. So you can see for the blue, this K is because maybe here the gradient of course will be constant because A is the algebraic difference between the two grades. Example, if this one is 6%, maybe this one is 2% minus 2%. So the algebraic sum will be equal to 6 minus 2, which will be equal to 4%. This will remain constant. So now, if now I adopt to connect from here, using the blue, the length of the curve will be longer. So K value will be high. If I connect from here with the red, so here the green L will be this. At the red L will be this. So you can see here we have this is A, this is B, this is C. So KA will be equal to LA over A, which is 4%. Then this is for this one. Then for KB will be equal to LB divided by A, because A is the same. A does not change because the gradients of the road is there. Then KC will be equal to LC over A. So where do we have the smallest K value? We have the smallest K value for LC. For LC, because the length of the curve is very small, and which means the level of abruptness here is too much. So the smaller the value of K we have, the difficulty of moving is experienced. I think you understand. And then, of course, the more the abruptness is being felt by the drivers. So that's why it is advised to have if you could have a long length of the curve, that is good because it will simply to simplify the driver doing the maneuvers and also foreseeing. Because imagine if you are just climbing just up to the point there, it is difficult. So the value of k will be defining the level of abruptness. This is to inform you about the case. So now, in some cases, instead of making this one as a parabola, we may adopt now to change a parabola with a simple circular curve. So in that case, we take the value of k and then we multiply by 100. That's what I was telling. Are you together, class? I know sometimes some people may not understand. As I have said from the beginning, today, due to some security reasons here in our campus, our offices, my offices are in Kanchigari, so the access was not easy to my office. Reason why I decided, they delayed and then I decided let's now have our class online, maybe at 10. So don't worry, when we will be back in a classroom, I will try to repeat this one for those who cannot understand. Actually, I could not come physically. That is beyond my. I am not the one who's deciding about the security matter. We should sometimes respect people. Okay, so I am sorry for not coming to class, but actually, I know explaining this one to you without being in a class is not easy. But security situation could not allow me the access. Then it delayed. So please note that the k value for vertical curves is a parameter which allows us to understand the level of abruptness, the measure of the abruptness of the curve. So the small the value of k, the difficulty to negotiate, the difficulty to go through it is experienced. So as you can see on the diagram, the blue, if we adopt the blue line, here we'll be having a very high value of k, which is good. Okay, it is very simple. Now, let us continue. I want to continue with my slides. Yeah, so this is what I was explaining. No, I did not share. Did I share? I think not yet. Let me share. Okay, I'm sharing. It is coming. Can you see it now? Is it available? Okay. So here, now what does it mean? Here, I want to mean that, so we have seen the purpose of k value. K value in vertical curves represents a measure of the curve's abruptness. Okay, so meaning that the higher k value will give us gentle curves, and engineers, of course, will be using values which are high. So if the k value is high, it is better for even the drivers, and also if you are moving. But if k value is very small, problems will happen because you'll be experiencing some difficulties. Now, there is a possibility. You remember I told you that the vertical curves can be either parabolic curve or can be circular curves. So there is a possibility of changing parabolic curves into circular curves when you're dealing with the design. So how do we do that? So there is a relationship or a correlation which exists between the k value and the radius. So the correlation is in such a way that the radius of the circular curve would be equal to 100 times K value of that design. Let's, for example, have an example. Suppose, let me come to this diagram. For example, suppose that we have a sag curve with the algebraic difference, which is, for example, 80%. And let us assume that the design speed is 70 kilometer per hour. So in that case, if it is 8, we are here, and then we are having the speed of 80 kilometer per hour, 70, sorry. So we are here. So meaning that our K value, you can see, our K value is 23. So now, if our K value is 23, and then you want to make now a circular curve, not a parabola curve, so we would say that a circular curve would have a radius of 23 times 100, which is 2,300. Are you together, class? That's what it means. Okay? That's what it means. Now let me continue. Yeah, these are some of the examples. So now, let me talk about some particularities of crest and sag curves parameters in Rwanda. In Rwanda, you remember we have got some classification. In Rwanda, we have got what we call our design standards, which have been developed by the Rwanda Transport Development Agency. So in Rwanda, we recommend that the minimum, you understand, the minimum length of vertical curves should not be less than twice the design speed for road class 1, and not be less than the design speed for road class 2. And this restriction is only for class 1 and class 2 roads. Let me try to simplify this. What is road class 1? You remember the classification of roads in Rwanda is based on the traffic volume. Those in the range of 15,000 and above traffic values. So what do we say? We say this: if you want to design a vertical curve in Rwanda and you have a design speed which is 80 kilometers per hour, the minimum length of the curve, if it is in class 1, it should be equal to 2 times 80. So how much is that? That one is 160. 160 kilometer, which is almost how much? 16,000 meter. 16,000 meters. So meaning that our vertical curve should not be less than 16,000. You know, 80 kilometers per hour is too much. If you're making a vertical curve which is very small, now the drivers will be experiencing too much kind of abruptness, because you know, the more the shorter the length of the vertical curve is, the small the value of K that you are having, and that's a problem. That's a problem. Okay, so now, and then for the roads in the class number 2, we have to make sure that the design speed, if for example it is 80, which is 80 kilometers, how much meters? I think it is 80 kilometers, almost 8,000. So it means that for class 2, we should not have a curve which is having a length which is less than the design speed for road class 2. Okay, so this you should note it down. These are some other guidelines. Maybe this one I will say. And then another guideline is that where we have the grade, which is less than 0.5%, you know the difference in the grade. So you take the G1 minus G2, for example, and it's less than 0.5%. So in that case, we can sometimes even not put a vertical curve. You understand? We can say for this, let us forget about the vertical curve. Then for roads in class 3, 4, 5, remember, the more you go to the lower class, the traffic becomes very less. So in that case, for those class 2, 3, 4, 5, there is no minimum length that is specified. So you can just design some vertical curves, crest or sag, anyhow. The good thing that you should do is to make sure that at least they are available, and but they are not specified in the design standards. Okay. Now let's go to the gradients. I know, I know maybe people are tired, so let us have a break of 5 minutes. Then I'll be back. Then you are talking about the gradients. You're talking about the gradients. Okay? So let us have a short break of just 5 minutes or 5 minutes, and then we'll be back, and then I'll talk about the gradients. But before you go to the break, note those things. Please note that the vertical curves can be either parabola or circular curves. And the vertical curves are being defined by the length of the curve, the design speed, and they are also defined by the K value, uh, which of course will be defining the level of abruptness. So now let's have a short break. Uh, then at 11:20, I will restart with the gradients. Hello, class. I am back. Let's talk about now the gradients. You know, as far as vertical alignment is concerned, we are having, apart from vertical curves, we are also having some issues or some aspects related to the gradients. You know, the gradients are complex and depend on the number of factors, of course. Sometimes the gradient may be too much severe so that maybe a particular vehicle cannot go up. Or a gradient, if it is too long, it may also harm. Also, it may render the situation very difficult. And then also, the gradients are designed based on the existing traffic composition. If you have got maybe a lot of motorcycles, commercial vehicles, trucks, lorries, for example, I don't know if all of you know a place which is known as Norvège. Sometimes when you are climbing from Nyabarongo, Ruriba, there is a settlement where we used to call Norvège. You know that road is known because of the gradients that we are having there. You know, in that place, if the traffic is made up of trucks and lorries, I think lorries will be very difficult for moving in through that road. But maybe trucks which are not too much loaded, they can go. So when we are making a design for vertical alignment, we have to take care of the maximum gradients and the minimum gradients. Normally, the maximum gradients are for the purpose of allowing the vehicles to climb. If the gradient is too much, vehicles may not be able to go up. Then, if the gradient is almost non-existing, also there is an issue or there is a problem of self-draining. You know when it is raining, water is on the pavement, and then sometimes we need the water to move. So that should be taken into consideration. So for this reason, normally the maximum gradient for very low vehicles of traffic flow, like these small vehicles, the maximum gradient can go up to 18%. 18, 18%. That's very steep. They can go up. But for this heavily loaded truck, normally the gradient should not go beyond 15 and 16. So there are some limitations about the maximum gradients and the minimum gradients. So the maximum gradients, this is to allow vehicles to go up. So the maximum, the very, very maximum is 18. And for small vehicles, or what you call four-wheel drive vehicles. And then for the heavy vehicles, you can go maybe up to 15. But we make sure that the gradient is not too long, so the length. There are some design tables which are provided by the Rwanda Transport Development Agency, and those tables are useful. I think because of the rain, I don't know whether if you are listening to me, because my place is raining. Are you listening to me? Are you listening to me, class? Okay. It's raining, but let me talk. No problem. I was telling you that the gradients, we should be careful of the percentage of the gradient, and we should be very careful of the length of the gradient. So this table, you can see there are some table which have been developed by the Rwanda Transport Development Agency, where we have got different terrains for urban, flat terrain, rolling terrain, mountainous, escarpments, and urban. So you have got different classes of roads, whereby We have what we call desirable values and the absolute values. Normally, for a flat terrain, the gradient should be like a 3%. That could be the maximum gradient. But if you have a 4, it's okay. It's absolute. For the urban or escarpment means downwards. You have a lot. But for road class 1. So for different classes of roads, there are some desirable values and some absolute values. So let me, I think I have to stop here because uh, I think the rain is too much. I'm going to share with you the link to fill your attendance, and please take your time to fill your attendance. And I think today, let me stop here. Maybe the remaining I talk it in a class physically, next class. And I may plan also for another week. If it is possible, we can plan for the site visit. I have planned the site visit, but where I requested, they could not respond. So I am still struggling to get a place where you can go for site visits. But for the next class, it will be a physical class, and let me share with you the attendance. So thank you, class, and take your time. Do not delete the others' attendance. You just fill it slowly. Okay? I'm sharing in a few minutes. So let me end it here. So thank you very much for attending, and please fill the attendance. I'm going to share with you.